This is an IoT network with randomly placed nodes operating with the RPL protocol. In this setup, we will have no direct communication with the nodes, but only via the sink, the green node, number one, via the serial port. This red node over here, we will see later on that it's an attacker, an intruder, and those are regular IoT nodes on the network. In order to communicate with the sink only, we implemented some cross-layer functions. Layers 2 and 3 are communicated on an application layer via UDP messages. More specifically, we have three main entities in this setup. This is the controller, Java 8 controller, which could be lying anywhere, somewhere on the cloud. An adapter lying on the host PC connected directly to the serial port with the sink. That's the only communication we had, as I said before. And an IoT network, IoT devices scattered among an urban environment, transmitting back to the sink information like temperature, humidity, dust levels, etc., etc. Now, this is a Contiki 3 operating system, and this is the Kuja emulator, and let's start it. Start the controller. Controller is two things, the graph interface and the output. It's waiting for the serial port to communicate. We start this network. It's waiting for the serial port here. As soon as the network starts communicating, we see the network graph. Let me make it better. Don't need this. Now, the initial information comes from RPL, from the sink and the RPL. Details of each direct neighbor of the sink are there, and there are messages which they have a pair of information, messages coming from each node to the sink per request. So the sink is waiting, it will communicate its neighbors. You see there are some red nodes over there. This means that those nodes for the moment were only reported by other nodes as parents. The nodes themselves did not answer yet. So the sink, now they answered. So the sink now made them, knows them. So the network graph is now complete. Over here, we have the basic information of the network, which is the UDP messages received by the sink, by the sink, from each node, and each node communicates ICMP messages with the sink. This is an optional thing, we can turn them on and off. The network still trying to set up, because RPL is still trying to find the optimal network. So it will most probably stay like this now, unless I do some radical changes. So remember that this is a many-to-one network, so each node has exactly one parent, no more no less, except the sink, of course. So it's very easy for the algorithm we constructed to make sure that incoming edges are the same number with the number of nodes excluding the sink. Over here you see we have 20 nodes and 19 edges. We're okay, 20 nodes including the sink. Over here we have how many UDP messages we received from each node, and when was the last time that the node communicated with the sink. This will help us later on to determine whether a node is dead because of its battery or under attack, or it's not communicating anymore with the network. RPL doesn't have such a function. RPL keeps as neighbors all the nodes previously visible to the node and does not remove them. Now let me do a radical change, do something like this, and see how the network graph will behave. It will take some time. Remember that RPL is not time intensive. Nodes do not communicate in real time, but rather after long periods in order to preserve energy. Now, how is this constructed? What's the intelligence in this? First of all, as I said, there are algorithms checking if a node, you see those nodes are suspects of being there. Why? Because their time, the last time they were visible is long ago. Look at this, please. This is a loop, and the network will find out about this and change it. How? We implemented algorithms again which are checking the network for all mistakes. This is something that will be taken care of a spanning tree algorithm. There is another algorithm which is checking for parents. If the node has exactly one parent, if the parent is still there, and whether this parent leads to the sink. You see this network is not correct for the moment because there are 20 nodes and 17 edges, so it means that something is wrong. There, eventually the network graph is concise again. If you go up here, you will see that the nodes were removed and spanning tree found the loop and reprobed the nodes in order to start checking again the correct parent. Now, this is an intruder which is inside. It means that it knows how to connect to the network and it responds to the sink's messages. So this is a rather serious attack. It means that the intruder knows inside. Somehow it has the source code of the Contiki operating system that the other nodes have, and will start attacking as a gray hole attack, which means that it will stop some UDP messages coming from the other nodes. In order to achieve this, it also implements a rank attack, which means that it falsely advertises a bigger rank, a closer to the sink rank than what it is. As a result, more nodes than those that it would normally attract will be its children, will prefer it as a parent. The problem here is that the node will have it as a normal, the network graph will have it as a normal node. Why? Because it participates normally to the network. When it starts attacking, we will see that the UDP messages of some nodes will start dropping. For the moment, it's only node 11, the attacker, that has less UDPs. We will also notice, we know from previous research, that the ICMP messages of the nodes under attack will change radically. And those are the two major things that we will keep on monitoring in order to find out the intruder and the attacked nodes. How do we know which nodes are under attack? We are implementing clustering algorithms, in particular k-means, to divide the nodes in two categories, those who are attacked and those who are not. And those who are attacked, we will further explore the possibility of dividing them in network cliques. So if there's a click between some nodes, those nodes are attacked by the same attacker, because remember, the attacker might be more than one. But this is a next episode.